So now we're going to talk about the physics of where this energy is actually going. Why does a cruise liner use more energy than a car or a bicycle? What's the energy actually going to do? Now when people start in this field, they often think there must be some equation telling me how much energy something uses to go a particular distance. But there isn't. In principle, it takes no energy to travel around the Earth's surface. You're not changing your altitude. In space, it can indeed take no energy to go huge distances. You just get going and drift forever. But on Earth, there are four main things where the energy is going to go. We're going to talk about them in turn, and then go on in future videos to show examples of how you calculate these for different forms of transport. These are kinetic energy, potential energy, rolling resistance, and drag, also called wind resistance. Okay, so kinetic energy. You're probably familiar with this, half mv squared. That's the energy you need to exert to accelerate something with mass m up to a speed v. You just get it by integrating. So you only need to put this in once. People sometimes tend to use this and assume it's half mv squared per second or something like that, but it's not. It's just once. So, for example, when a car, the traffic light goes green and you accelerate your car, you use half mv squared worth of energy to get up to your cruising speed. It can then stay at the cruising speed with no more kinetic energy needed. Likewise, a rocket accelerating up to an orbital speed will exert that half mv squared to get up to that speed, and that's all you need. But then there's potential energy. If you're staying on the level, you don't use this, but if you want to climb, then you need energy of mgh, m the mass of the object, g the gravitational constant, 9.8, and h the height change. So for example, an airliner climbing to cruising altitude, like you see over here, that'll need mgh to get up to 10,000 meters where it typically flies. If you're riding a bicycle up a hill, you need to exert this energy to go up the hill, or walking up a mountain. Hopefully that should be familiar to you. Then there are two things which may be a bit less familiar. One is rolling resistance. This is kind of like friction, but there are very few vehicles that actually need friction to calculate anything. Maybe a sled on the ice skating or skiing maybe, that's friction as you slide along the surface. But most things that move along a surface use wheels, and rolling resistance is the wheel equivalent of friction. It comes from the fact that as you rotate your wheel, they deform. They flatten out at the bottom, the rubber in a tyre bends, and also the ground underneath might bend, especially if you're on a soft thing like trying to ride a bike on a beach. So it's some combination of the bending of the wheel, the tyres, and the bending of the ground underneath it. And the equation for it is actually very similar to the normal friction equation, which is saying that the force is equal to a coefficient, called the coefficient of rolling resistance, times the normal force, which is how hard the vehicle is pushing into the ground, which for most purposes is the same as the weight, so it's mg. So something weighs 100 kilograms, it'll be 100 times 9.8, so 980 newtons. Multiply that by the coefficient of rolling resistance, and you get the force that opposes the motion. For a car tyre on a flat pavement, it's about 1%, and very different for different other purposes. That tells you the force. We're more interested in the energy. Energy is work done, which, as you may remember from your physics class, is equal to the force times the distance. So energy equals the force, the coefficient times normal force, times how far you're exerting that over. We also sometimes care about power, which is energy used per unit time, which is equal to the force times the velocity. So this equation here. And then finally we get to arguably the most important, wind resistance or drag. On Earth, when we travel somewhere, we are travelling through an atmosphere. Or if we're swimming, we're travelling through water. And that causes a problem. Imagine, for example, a car. As it drives along, it's sweeping out a volume of air, and all the air in that volume has to get out of its way. Of course, it's a bit more complicated than that. It's not as if the air in that thing disappears. The air here will have to swirl around the car, and the air outside will be pushed as well by a bit. But you can approximate it as saying all the air in this region that the car is going to sweep through has to get out of the way. So how much air is that? Well, it's going to be the volume of this per second. It's going to be the area times the velocity. So the mass of air is going to be the volume, which is velocity times area times density of air, which is about 1.2 kilograms per cubic meter at sea level, about 7% less than that in Canberra. So that's how much air you have to get out of your way, but it's also how quickly you have to get out of the way. If you're travelling fast, the air has to be moved quickly to get out of your way. So the net result is that the drag force is proportional to the velocity squared. One factor of v because if you go fast you have to get more air out of your way. A second factor because that air has to get out of the way quicker when you go fast. So the drag force is going to depend on the mass you push out of the way times velocity squared, with some constant which is going to depend on the complicated fluid dynamics of exactly how the air swirls around your moving object. For historical reasons this is given a half. So we've got what's called the drag coefficient, which varies from something like 0.1 for something very streamlined like a bullet train. It's typically about 0.3 for most cars, up to about 1.2 for something very unstreamlined like a person riding a bicycle. So that's the force caused by drag. Technically this v depends on the relative speed of you and the wind. So if there's a headwind, v becomes bigger by that. If the wind's coming from behind you, it becomes less. But for the moment, let's assume a stationary air you're going through. Energy is just this times the distance, just like we saw before, so just multiplied by distance. And the power is this multiplied by the speed. Because the distance travelled in a second is your velocity. So that gives you proportional to density times volume cubed, and that might be a familiar equation from you because it's also pretty much the equation for the energy from a wind turbine for exactly the same reasons. It's the rate at which energy in wind sweeps past the place. In this case it's you that's moving, not the air. So those are our 4 forms of energy, and in the next few videos we're going to talk about how you actually calculate these in different forms of transport.